A warm welcome to the third part of the basic concepts of astrophysics. These basic concepts, which are both of astronomy and astrophysics, will help you for a better understanding of the subject when you go and study the mathematical part as well as delve deeper into these concepts. These basic concepts will create a fundamental understanding of the subject. Now, in this third part, as you see, I have written on the thumbnail, it is astrophysics. Now, you might have a question in your mind. There is something which is also called astronomy, and is there at all a difference between those two, or do they bear the same relationship? Let us find out in the first part of our video what is astronomy and astrophysics, and do they have the resemblance or do they have any difference between them? So first, let us see that how we study the object. So in case of astronomy, it is a scientific study and which studies what? The stars, the planets, the comets and the galaxies. Now when we study those objects, what we see is the observation. So astronomy actually includes observational and theoretical aspects, and they basically focus on the position and motions of the stars, planets, overall the celestial objects. And how do we observe them? We use telescopes. So using telescope in astronomy and other instruments are used in order to gather data, in order to measure the luminosity, the brightness, motion and composition. And who does all those measurements? They are called astronomers, and astronomers use powerful tools like ground-based or space-based telescopes, satellites, etc. to collect data on celestial objects. So this is what we can call is an astronomy. It is a scientific study which basically studies the celestial objects and makes observation and on the theoretical aspects. Now what about astrophysics? Now, as you can see, astrophysics, the word itself uses physics. So it uses the principles of physics to understand these celestial objects and phenomena. As you can see, definitely uses physics like gravity, nuclear fission and different other physical phenomena and models which includes electromagnetism and others. And who are the people who do these things? They are called astrophysicists, and they are a special type of physicist who studies the basic workings of the universe on the scale of stars and planets. And as you can see that why do we do that? Because astrophysics explains or aims to explain the why behind all these astronomical observations. So the why part is being addressed by astrophysics. Now, now that you understand the basics of astronomy and astrophysics, here comes a kind of a distinction or relation between them. First, if I go by the scope, you will see astronomy actually encompasses the observation and study of celestial bodies and phenomena, where on the other hand, astrophysics focuses on the physical properties and principles and uses the physical law to govern and understand these celestial objects. If I go by the method, astronomy uses the method of using telescopes and other observational tools, and in astrophysics a lot of mathematical models, simulations and other theoretical frameworks and models are used. If I go by the approach, astronomy includes both observational and theoretical aspects, while astrophysics mostly focuses on theoretical modeling and applying physical principles to understand this physical phenomena. Celestial phenomena. So overall we can say is this: there is a significant overlap between astronomy and astrophysics, with many astronomers can also become astrophysicists. So the distinction lies in the primary emphasis, which is observational and descriptive, which is astronomy, and using theoretical and physical models, which is astrophysics. So that is why my video, as you can watch in this, is both an overlapping between astronomy and astrophysics. So here comes the bottom line. We can call that from a non-academic viewpoint, I would consider astronomy to be a general label applying to the study of celestial objects, in order to say that you could think of astrophysics as the study of how these objects work, which I mentioned. And the practical distinction between astronomy and astrophysics at points gets very blurry, because in many universities there is no real distinction between the fields. A graduate astronomer from an university would have roughly the same training as a graduate astrophysicist from another university. So there are overlapping factors. However, we have seen what is the relation or distinction between astronomy and astrophysics. Now, as we say, astronomy and astronomy observes things, how the celestial objects they behave and the luminosity. One of the greatest wonder which happens in the night sky is this one. Let us understand now the difference or the relation between what is called a red giant and what is called a red supergiant. We will first start with the red giant. So if I go by the definition, it is a late stage star in the life cycle, and it has got I would say medium mass star like our sun. And if I go by this size, then it grows much larger than its original size. Almost it becomes 100 of times wider than that of the sun. The nuclear fusion actually takes place in this way, that hydrogen in the core is depleted, forcing fusion to occur in a shell around the core, and the surface temperature, oh wow, it is quite high. It can go up to around 5000 Kelvin to make it appear reddish. So as a sequence, a red giant star sheds out layers to become what you call a planetary nebula, and it leaves what is called a dwarf core. So overall we can say a red giant is this. It is a luminous giant star. It has got a roughly 0.3 to 8 solar mass. The outer atmosphere is inflated and tenuous. It makes the radius large, and the surface temperature is around 5000 kelvins. As a result, the appearance of the red giant star from yellow to reddish orange. This is a very extraordinary phenomena that happens. Now, if I take a red supergiant, then by definition, what we can say is that it is also in a late evolutionary stage. What was this one? Let us see. It was at a late stage, but it is here, it is much more at a later stage. And this is much more luminous and larger than a red giant. It has got a huge, gigantic size. That means it grows much larger than red giants. The nuclear fusion actually uses like helium and carbon at its core. That means it has got heavier elements. Surface temperature around 5000 kelvins. And this red supergiant leads to an explosion, which creates a kind of a supernova, and it might leave behind a neutron star or a black hole. So overall we can say is this, that red supergiants, or RSGs as they're abbreviated, are stars with a supergiant luminosity, and they are the largest stars in the universe. For example, Betelgeuse and Antares A are the brightest and best known red supergiants, indeed the only first magnitude red supergiant stars. So you can further classify, however I have not got into this. So what is the relation or the difference between them? If you go by mass, then red giants are generally low, 0.3 to 8 solar mass, and these red supergiants are often huge, massive. If I go by the size, then you will see that red giants are large compared to the main sequence phase, but red supergiants are significantly large, sometimes extending beyond the orbits of Jupiter or even Saturn. If I go by the luminosity, then the less luminous, these are very much luminous, and red giants ultimately end as white dwarfs, but this ultimately leads to a explosion which creates a kind of a supernova. So what would be the defining factors of red giant and supergiant? Obviously the first would be the size, because immense size of red supergiants which can become hundreds of thousand times larger. Definitely the mass is a defining factor, because red supergiants are much more massive than red giants, influencing their evolutionary path, such as supernova explosion or formation of neutron stars or black holes. And yes, luminosity. Red supergiants are extremely luminous, often among the brightest stars in the galaxies, while red giants are not as luminous as supergiants. Now, among these red giant and red supergiant, what we are also interested is when it happens in the night sky, there is something which is called a galaxy and a nebula. Let us look into the next part of the video. What is a galaxy? By definition, it is a massive gravitationally bound system, and it has got many elements. For example, stars, the stellar remnants, the dark matter, and various other astronomical objects. The structure, how does it look? Yes, it comes in elliptical, spiral, irregular, and there are different types of galaxies which I have not covered here. Now, it also is gravitationally bound. That means it is held together by gravity, galaxy, and it actually contains nebula. That means nebula are actually found within galaxies, which forms the area where the stars are being born. This is what is called a galaxy. If I go by nebula, then you see these are actually gas and dust. So a giant interstellar cloud composed primarily of hydrogen gas and helium. The nebula types are different. For example, emission nebula, which is glowing, reflection nebula, reflecting light, planetary nebula, shells around dying stars, are different types of nebula which can be classified. The next, which is important, yes, their sizes do vary because they can range from vast regions, hundreds of light years, to small, denser clouds. And this is the birthplace, I would say, the cradle of star formation. Because of the giant molecular clouds, they are dense for gravity to overcome pressure, triggering what is called a star birth. Now, there is some important relations and differences between galaxy and nebula. The size galaxy are huge, enormous, typically spanning thousands to hundreds of thousands of light years across. Nebulas are not much that bigger, especially a few hundreds of light years. They are much more complex. By complex, I mean the overall structure, the gravitational distance, etc. They are quite complex. Nebula, I would say their internal structures due to local processes are much smaller than compared to that of galaxies. If you talk of star count, you can see this has got a few billion to over a trillion stars. But nebula is not that much. It has a few thousand stars. In terms of chemical composition, it contains stars, gas, dust, dark matter, a lot of things. A nebula is primarily composed of gas and dust. If I go by the function, I mean to say how a galaxy functions, you will see that it is a self-contained system. But nebula are basically a part, that means it includes the galaxy structure and definitely plays an important role in star formation. The evolution process tells that galaxies live much longer. That means they evolve over billions of years, influenced by mergers, etc. This has got very shorter lifespans compared to that of a galaxy with specific stages of stellar evolution. If you talk of the visibility, then yes, you can see by telescopes a fuzzy patch or well-defined spiral. You can see the outer arms of elliptical galaxies. But nebulas are usually observed as smaller, or I would say colorful patches. It is difficult to observe. Now, what are the defining factors of galaxy and nebula? The first is this one, the size. It is much, much bigger. The galaxies, they are much more complex system. Nebulas are, I would say, smaller, and they have a highlight of specific process, and they are important for star birth. If you want to read through it, you can just pause the video and go through that. As I told you, size, galaxies exhibit a wide range of shapes and sizes. Nebulas showcase diversity in colors. And cosmic significance, galaxies are the fundamental in understanding the large-scale universe. Nebulas actually provide much more insight if you want to know how a star is born or stellar birth, which actually enriches and evolves our understanding of interstellar medium. When we talk of galaxy and nebula, there is another very important concept which comes is the black hole. But hold on, I'm not going to talk about black hole, but something much more significant and important than black hole, which is called an event horizon, and what is the Schwarzschild radius. Now mind it, these are very close concept, but however, a close look will help you to understand better. Now, if I go by the definition, you see event horizon is basically a physical, I won't say physical, but it's a boundary. That means you cannot go beyond the black hole, you're doomed to die. So no light or any other forms can escape. So you can think it as a one-way membrane. That means you can fall into, but you cannot actually get out. And this is actually a point of no return because nothing can come out of that. So that is why it is black. And the singularity in that part is hidden because event horizon actually hides the black hole singularity, which is a point of infinite density. We really don't know what happens at the singularity. Researches are going on, but it is said that the laws of physics breaks down. This is what is called event horizon. If we talk of Schwarzschild radius, you will see this is the formula, and it actually is a mathematical model. It is a distance which says that beyond which or if it is of a Schwarzschild radius, you can bring that object to a black hole. It can be a car, a body, a monument, a building, anything. So it is basically used for a theoretical calculation, because the radius of a sphere, that if a mass were compressed within that sphere or that radius, Schwarzschild radius, it will become a black hole. So it is used basically the distance from a black hole center at which the escape velocity for any object equals to the speed of light. And remember that it is not a physical barrier, it is just a mathematical calculation which was named after the brilliant German mathematician Karl Schwarzschild. And I have already made a video how he framed when he was deployed as a lieutenant in First World War, and he wrote the first exact solutions of Einstein's field equation, staying inside the bunker where the war was raging at full force, and he wrote that letter to Einstein, and Einstein was thrilled and amazed to find how under such condition can a brilliant mathematician like Karl Schwarzschild frame the first exact solutions of Einstein's field equation, and that is what is called the Schwarzschild radius. Very important relations come up. The first is that event horizon is a boundary, although not physical, that no information can escape, whereas this is a radius which is applicable for a non-rotating black hole. The nature is conceptual. This is used for theoretical calculations. If you go by the scope, then event horizon applies to all black holes. That means rotating, non-rotating, charged, uncharged, spherically symmetric, non-symmetric, etc. But you see, when Karl Schwarzschild designed or found out Schwarzschild radius, he did it for non-rotating uncharged black holes. That means these are called Schwarzschild black holes, and it eventually comes from Schwarzschild metric. So these are ideal conditions. So existence is an actual boundary. This is actually derived, just I was talking, from the metric, Schwarzschild metric. So the derivation defined by the conditions of general relativity, and this is derived from the Schwarzschild metric. If I further go into the relationship, you will see that it marks the point of no return, and it determines the event horizon of a specific black hole. Gravitational effects prevents any form of radiation or matter, although Hawking radiation is something different. It defines a theoretical boundary, and it definitely depends on mass. Event horizon depends on the mass, the spin of the black hole, but this is directly proportional to the mass of a black hole, and this is how it is. So what are the defining factors that we can find? Very simple, you can look into this diagram, and it simply says that it is the no point of return. And it is a region of space-time where the escape velocity exceeds the speed of light. That means you need to have a escape velocity more than the speed of light, which special relativity prevents us. And the event horizon is a real physical boundary, but because of extreme gravity, we cannot directly observe it. If you talk of what is the Schwarzschild radius, this is the formula, and you can see that it represents the distance from the black hole center. So if now what I was telling, that if a star collapses within its Schwarzschild radius, it eventually turns into a black hole, and the Schwarzschild radius becomes the event horizon size. So there is another concept which you might have heard, what is called a Chandrasekhar limit, which I have explained in the first or second episode of this series on basic concepts of astrophysics. So Schwarzschild radius is basically, remember, it's a tool to understand when a collapsing object will inevitably become a black hole. Anything falling within that radius will eventually turn into a black hole. You, me, object, the universe, and everything. The next and the final very important concept which emerges are called baryonic matter and non baryonic matter. Now, what is a baryonic matter? By definition, it is actually matter that we see around us. That means it consists of neutrons, protons, and atoms and molecules. Obviously, the total mass of baryonic matter is about 5% of the total content of the universe. What you see around, familiar matter, that means the star, planets, organisms, you, me, everything, that is basically the baryonic matter. And if you talk of the composition, then baryon is a type of a composite subatomic particle. If you delve deep, then it will contain certain quarks, and baryons belong to what is called the hadron family of particles. I'm not going into that, it's a part of the particle physics. So what you see around is the baryonic matter. What you don't see is what is called the non-baryonic matter. So it is a matter that does not consist of protons. For example, dark matter. So it includes dark matter, which is believed to take up around 27% of the universe content, and dark energy, which is around 68%. So the rest of the 5% is the ordinary matter. So it can be divided into dark matter and cold matter. As you can see, cold matter refers to dark matter particles that are, I would say, relativistically moving slowly, and non-baryonic matter cannot be observed because they do not interact through electromagnetic radiation and cannot be inferred from what is called gravitational effects. So what is the relationship between them? So baryonic matter actually consists of protons, neutrons, and they are not made of that. So what do you see? The kangaroo, the lion, the horse, the tiger, and everything around us, the planets, stars, galaxies, they are baryonic matter. And non-baryonic matter is something like this, which consists of dark matter, dark energy, a part of it, not the ordinary matter. It is observable definitely, but non-baryonic matter is not directly observable through electromagnetic radiation, and this one interacts, the baryonic matter interacts with light and other form. That is why it is visible, and here it does not interact. Contributes to the other structure and dynamics of galaxies and influences the structure and behavior of galaxies of the universe through gravitational effects. So what could be the defining factors of baryonic and non-baryonic matter? One is the composition, because baryonic matter is made up of atoms and molecules, and non-baryonic matters includes dark matter and dark energy. The baryonic matter interacts with electromagnetic radiation, that is why we can see them, and non-baryonic matter does not include any interaction with electromagnetic radiation. So it is very difficult to detect through any gravitational effects, and the presence in the universe, it consists of a small fraction of the mass energy content, while non-baryonic matter makes up the majority. So that completes our third episode in understanding the basic concepts of astronomy and astrophysics. So I would like to thank you very much for watching this video. If you have liked the video, please don't forget to click on the subscribe and click on the bell icon to get all the notification from Physics for Students. This is my email ID, which I always respond to your mail, and this is my other channel on general theory of relativity, which you can subscribe. You can follow me on my Facebook, LinkedIn, Instagram, and Twitter account. Physics for Students will be soon back with more and more interesting videos. See you till then. Goodbye.